Let's do the ice table review, and then we'll jump back into this discussion. So we have the Henderson-Hasselbalch equation. Some of the problems that you have been encountering are a little bit more challenging because they deal with chemical equilibrium without much of an explanation as to what species are important and what chemical species are to be ignored. So, and again, if you have seen this before, or if you learned this in general chemistry, feel free to help. We may need that again. But let's look at a problem with some interesting features that may help you make decisions when you are trying to solve a question. So we're going to look at a weak acid dissociation, and this weak acid is going to be nitrous acid. So this guy is going to yield that proton to water. So you're going to have H3O plus NO2 minus. Now, this being a weak acid is not going to completely dissociate in that. The equilibrium is actually shifted to the left, but we don't know where the equilibrium is shifted exactly. We do have, however, the value of the Ka. And the Ka for this one is 4.5 times 10 to the negative 4. So the Ka for this particular reaction is 4.5 times 10 to the negative 4. Remember that the larger this number, the more this is dissociating, okay? So if the Ka was times 10 to the negative 1, then the acid would be stronger. Now with that, let's say that we want to calculate the pH of a solution that starts with 0.45 molar HNO2, and it also starts with 0.4 molar NO2. So these are the initial concentrations of those two species. The water is liquid, it doesn't count. This one at the beginning contributed by the HNO2 is 0 because we haven't mixed the two together. So there are these things called the ice tables. Do you have a recollection of using them at all? No? No? Ice tables? No? Okay. So ice is simply an acronym for initial, change, and equilibrium. You don't have to use an ice table every time. Sometimes you have to make the call based on the problem that is given to you. But this is how you use it, and it's actually important that you know. So what we're going to do is create the ice table here. I'm going to put the initial concentration here of the species in this reaction are 0.45 molar. This one doesn't count. The concentration of H3O plus is 0. Now, it's super important to realize that that is really not 0. It's 10 to the negative 7 if you remember, because water contributes something. But the 10 to the negative 7 is so small that we're going to say it's 0. Because the contribution of this is going to be greater than the contribution of water. And then the initial concentration of the nitrite ion is going to be 0.4 molar. Now you mix them. And as you mix them, a certain amount of this guy is going to dissociate. We don't know how much yet. So we're going to put something called the change. And we're going to call the change by which this dissociates X. So this is going to give an X amount of protons, of H pluses. Because these are equimolar, one of these gives one of these and one of that, we can also say that the change in concentration of these is going to be 0 plus X. It's going to be generated as a product. And again, whatever this generates is going to be added to this. So this is going to be 0.40 plus X. Now, what happens to this amount if I'm calling it a certain dissociation amount as being X? Well, I need to make sure that I know that I'm subtracting that from here. So at equilibrium, once things settle, this amount is going to be 0.45 minus X. This one still doesn't matter. This one is going to be X, and this is going to be precisely that, 0.40 plus X. That is at equilibrium, once the equilibrium is reached. So these are the numbers that we're going to need to calculate the pH, because what we need to find out is this value. How much is that? That's what pH is defined as. pH equals negative log of H3O plus concentration. So I'm going to put it over here on this side. There are a few assumptions that are important to make. And those assumptions are going to be critical to different problems, but in this one I'll show you what it means. Okay, by definition, we know that the Ka equals, remember, we did it for water, we did it for a weak acid, is going to be the concentration of the products, these guys. So it's going to be X times 0.40 plus X divided by, water doesn't count, this concentration, 0.45 minus X. Okay? So that's just coming from Ka equals concentration of H plus times NO2 minus divided by HNO2. That's where that comes from, okay? Yes?
So the X is the hydronium ion?
Yes, the X is the concentration of H pluses. Because it's this H that is coming off, but we don't know how much. Now, we sort of have an idea because we have a Ka. So we know it's going to be a certain amount. But it's not exactly this. It's given by that and that amount. Okay? At equilibrium. So here comes the leap of faith. You need to make this assumption click. Under these concentrations that we're dealing, the value of X, whatever that ends up being, is going to be many times smaller than the concentration of the HNO2. So much, much smaller than 0.45. I mean, I don't know if it's going to be 0.00002 or 0.00005, but it's going to be much smaller. And we also need to realize that the value of X, whatever it comes to be, is much, much, much smaller than 0.4. If we don't make this assumption, we can still solve the equation, but it's going to be a quadratic equation. I don't know if you guys remember your quadratic equation from math. It's solvable, and nowadays it's even more so with all of the calculators that are equipped with artificial intelligence. But this is a very useful approximation because the number is going to be meaningless, just as we did it for hydrochloric acid when it was very dilute. Here the value of X is going to be so small compared to that when you subtract it or add it to this amount, doesn't matter. By itself it does, because it's going to determine the pH. So with that assumption, we rewrite this equation as follows. We say Ka equals, well, X, we cannot ignore it there because it's by itself, right? But here we can ignore it. So we're going to assume that that is so small that if we add it and is of that value, it doesn't matter. So I'm just going to not bother including it in the final equation, and I'm going to multiply that by 0.40. I'm done with the plus X. Again, if you want to leave it there and see how this takes you to a quadratic equation, do it. It's a good exercise. But we're going to get a value so close, without the quadratic equation, there is no worth the effort. And then the same thing for this. Concentration of 0.45 minus X, I'm going to ignore it, and that's that. So now I know the value of Ka is 4.5 times 10 to the negative 4. And if I just simply solve for X, now I'm going to have the concentration of H plus, of hydronium. So that is going to be, that is 4.5 times 10 to the negative 4 times 0.45 divided by 0.40. Can you please do that operation and share what you get? So what's the value of X? And of course, I'm going to be checking to make sure that you're getting it right by comparing your answers. Bless you. Why do I have such a long password? 224. No, 929 777. Oh, there's an announcement there that may be important to you guys. It says today, between 12 p.m. and 8 p.m., students will be unable to access services through Access BCC Student Services tab, as well as some quick links while we perform necessary updates to our systems. Okay, just wait until after 8 p.m. if hopefully there's nothing that you need that is urgent. Okay, so what number are you guys getting? I need two identical answers.
5.1 times 10^-4.
Is there a second person who got that? Excellent. All right, so now that we have X as that, we know that that is actually the concentration of H+. So now we can get the pH simply by saying negative log of that number, and you get an answer. And how did the ICE table help you? Well, you're going to see it with some of the homework problems. We'll take a look at a couple, or at least one, and see if we can use an ICE table to answer those questions. So the pH is going to be what, about it should be between 3 and 5.
3.3.
3.3? Yeah. Okay, good. 3.3 sounds about the right answer. This is a weak acid, but it's not that weak because it has Ka, less than 7, which makes it acidic. All right, so let's take a look at some of the problems in the homework. And I hope we did not lose our ability to project. I don't think we did. Okay. Oh, I'm connected. What am I doing? Here I was trying to connect it. All right. By the way, any of these deadlines can be moved. You don't have to worry about About it, just tell me, I need extra week or two, and I'll be happy to extend them. Okay. Solubility in water. Is there any problem that you want to start looking at rather than looking at all of them?
Number 5, I guess?
Number 5, okay.
Yeah.
Wow. Okay. This is not an easy problem, but we're gonna try to debunk it a little bit. So let's take our acetylcholine here, and what is it acting as? So we have nothing much here, a positive charge here, which became what? Let me see. Yeah, it looks like it's losing this part of the molecule, which is being generated as acetic acid, okay, or acetate, okay. So what is this number helping us realize? Let's see. You incubate the sample with the acid dissociates to yield acetate. Okay, so they're not showing this part or where it came from. They're basically saying that the acetic acid came from here, is not showing here anymore as acetic acid, is showing as acetate. So the acetic acid, let me just read it one more time. Right. So there's a wording here that is important to realize. Sometimes terminology helps you with part of the problem. Whenever you see the ending IC, it implies that it has the proton still connected to the conjugate base. Whenever you see the ending ATE, you actually have the conjugate base. So this is the conjugate base. And this would be the acid, the HA. So the acetic acid associates to yield acetate and hydrogen ions. At the end of the incubation period, you measure the pH again and find that it has decreased to 6.46. Okay. Now, from here you can see that the molar relationship between this and that is 1:1. One acetylcholine gives one acetate. All right? Now, we could use an ice table, and we are given actually an amount in volume which we're going to use to calculate the concentration later. But they want actually nanomoles in the original sample. So we need to work in reverse. Let's see the change in pH first. This one is going to take us probably the rest of the class, by the way. Because the change in pH is going to tell us the amount of H plus that was generated, right? So we have an initial pH of 8.37, a final pH of 6.46, a delta pH of, and here, the negative sign is not going to matter, but is simply the amount of H plus that was generated. Okay, I don't need the screen anymore. We have all the information that we need. I'm going to need the board. Do you guys have access to the problem right now? Can you look at it? Okay, so I'm going to change the page here. So what is the difference between those two guys? I mean, we could actually convert these to hydronium ions and then subtract the two, and that will give us the difference. But let's just get the difference as it stands right now.
1.91.
Okay. Now, that is the change in the amount of H pluses from beginning to end. Okay? Now, we're given a volume of 22 milliliters. The 1 nanomoles of the substrate. So in biochemistry, the reactant is not called the reactant, it's called the substrate. In this case, the acetylcholine is the substrate of the biochemical reaction that is going on here. Okay. What else? What other information do we have? Am I missing anything from the reading? Let me go back to the problem. Concentration. So this change in pH should be, or better be, equal to the change in concentration of hydrogen ions. So let's do that over here in front. So please do me a favor and give me the concentration of H plus at the beginning. What is the amount of H plus at the beginning of the reaction? How do you do that? The antilog of the pH. Remember that we had an equation. Let me erase this stuff over here. We never did a problem like that, by the way, in my introduction to pH, but this is going to force us to do it. I did have the equation on the board, but we never used it. So to get the concentration of H plus, you need to do the following. 10 raised to the negative pH. That's called the antilog. So what is the antilog of 8.37? And again, as always, I want two answers to coincide. Not because I want it, but because it's necessary so that we know that we're doing things right.
I got 4 times 10 to the negative 9.
Okay, that sounds about right because of the value there. 4 point what?
Just 4.0
4.0 times 10 to the negative 9 molar, okay? And what is the final concentration of hydronium? So we're going to do the same. This time it's going to be initial 10 negative, what is it, 6 point what? 6.48? What do you guys get? 10 to the negative 6.48. 3.3 times 10 to the negative 7?
I kind of wrong. Mine was 3.47 or 3.5 times 10 to the negative 7, so it's pretty much the same.
That's a sizable difference.
Because on yours, when you put it up, it's actually 6.
Oh, that's a different number?
Yeah, it's actually 6.46, but you have 2.48. But we can do the number.
Okay. So when I had it on the screen, it was 6.46, not 6.48? Oh, sorry. So then it's 3.5, right? My apologies to both. Okay. So there is a difference in the amount of hydrogen that was generated. So we can actually subtract these two to get the delta H, this guy. So go ahead and get final minus initial, and we're not going to care about the sign. So this is going to be an absolute number. I'm going to erase this too. I think I need the space. This subtraction can be a little tricky, but I want everybody to practice it. So we're subtracting 3.5 times 10 to the negative 7 from 4.0 times 10 to the negative 9. So let me see, 0.00000. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And 2.000000. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the differences between those two, I mean, do it in scientific notation, of course, because we want to make sure that we get the same answer. I think it's going to be 5 times 10 to the negative 8. Let's make sure that we all get the same answer.
Actually, that doesn't make sense.
What are you getting?
I get pretty much 3.5 times 10 to the what is this? Which is not, that shouldn't be happening. So that's what I keep getting to.
Well, then if the two of you are getting it, then that must be right. So we have concentration of hydrogen final minus the concentration of hydrogen initial. That gives you the delta. The difference shouldn't matter whether we subtract one from the other because it's a delta. And again, this was my poor attempt to transforming this into decimals. I don't know if I did it right. Let me put my mind to it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that is correct. And 1, 2, 3, 4, 5, 6, 7. That is correct. So if I put the two together, 0.000000035. 1, 2, 3, 4, 5, 6, 7, 8. No. 3, 5, 0. Unos cuantos 6, 4, 3, 3.46 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. That's not what you're getting?
Yes, that's pretty much.
3.46 times 10 to the negative 7. All right. So what we have accomplished now with that reaction going on an equimolar basis, we now know how much hydrogen was produced, right? The difference between the final and the initial is the amount of hydrogen that was released as acetic acid. So now we had to do something with the volume that they gave us and the concentrations that we have. So these have values, let me see if I can put it here, of moles per liter. So we're going to write 3.46 times 10 to the negative 7. Instead of saying molar, we're going to say mole per liter. But the volumes that we were given were in milliliters. And the volume of the sample was originally, I erased it, 22 milliliters? 22 milliliters. So we don't have a liter. We have to convert these 22 milliliters to liters. And then we'll see what we do with that. So the volume equals 0.022 liters. I did that on my head. Please correct me if I'm wrong. It's 22 divided by 1,000. Is it 0.022?
Yeah.
Okay. So now that is the volume in liters that we have. And what essentially we have left to do is this conversion to nanomoles. Okay? I'm looking for the conversion. Is it 10 to the negative 9? Let me look it up. So we need to calculate the number of moles using this number and this number. I'm going to move it over here. I don't need that anymore. So I have the amount of hydrogen produced, 3.46 times 10, times 10 to the negative 7 mole per liter. How many moles is that? Well, I don't have a liter. I have 22 milliliters, which is equal to 0.022 liters. So let's find out the number of moles that I have. So if we multiply those two numbers, the resulting number is going to be the number of moles of hydrogen produced, which is equimolar to the number of moles of acetylcholine that was degraded. Okay? So 3.46 times 10 to the negative 7 times 0.022 liters. I'm sorry. I forgot that I already wrote cancel out. Okay. Please, two answers that agree. You know what? Now that I look at the problem, it's not as difficult as I thought it would be. Easy for me to say, but I did look at it and it's like, what? Well, if I did that, I cannot imagine what you guys did. So 3.46 times 10 to the negative 7 times 22 is going to give us the number of moles of hydrogen produced. Anybody wants to share an answer? Did you figure that, Jonathan, or are you still stuck on that? Oh, now you're in the problem. Good. You have different numbers, though. So make sure that you calculate it. I guess every time the problem is generated, it gives you different numbers. So please do the problem as we are doing it, but with those numbers, and let's make sure that we get the right answer. If we can accomplish that, I'll be very happy, because that will put you on a better footing. Not that you need to make me happy, by the way. I'm sorry for making dumb comments like that. I'm still waiting for an answer.
I got 8 times 10 to the negative 9 moles.
8 times...
I got 7.61.
7.61? 7.61 times 10 to the negative 9?
Yes.
And the units are mole? Perfect. We're one step away. Let's review what we know. The conversion of acetylcholine into choline generates an equal molar amount of acetic acid, which results in producing H+. The amount of H+ being produced was calculated by subtracting the initial pH and the final pH. That gives you how much H+ was generated. Because the amount of H+ generated is equimolar to the amount of acetylcholine consumed, this is actually the answer. But unfortunately, they want it in nanomoles, right? So we just have one more conversion to do. So we're going to say 7.61 times 10 to the negative 9 mole times a conversion factor that relates moles to nanomoles, and is 10 to the negative 9. So 10 to the 9th nanomoles are 1 mole. Right? I may have to look it up. Okay, micros 10 to the 6th. Nano is 10 to the 9th, yes. So that cancels moles out, and it's going to leave us with nanomoles, 7.61. That's it. So that's the answer, 7.61. At least to the problem with these numbers, which may be different, and this volume. So please, before we change problems, repeat what we just did with your own numbers. I'll give you the 5 minutes that you may need, or the 2 minutes that you may need, and let's make sure that you get the correct answer. In the next chapter, we're going to work with amino acids, and amino acids are a little tricky. So let me leave you with an idea that may help you with chapter 3 and the homework problems that you're going to have. Ashley, I think we discussed this briefly on my office hours, so please forgive me for repeating it. But here it goes. I think it's one of those other topics that I wish books would make very clear from the get-go, instead of tricking you into understanding things that are a lot easier to understand if they are explained instead of hidden. So bear with me for the next 10 minutes, and then we'll be done. So in the next chapter, we're going to talk about amino acids. And in the simplest term, an amino acid has the following ingredients. It has a central carbon connected to two functional groups, and then two other things that are not relevant for this introduction. I'm going to use the simplest of all amino acids, which is glycine. So glycine has a hydrogen here and a hydrogen there, and then the functional groups are as follows. There's a nitrogen there and a carbon here. The nitrogen here is an amino group. The carbon here is a carboxyl group. So you remember your carboxyl is a carbonyl carbon, C double bond O, and then connected to an oxygen, which is then connected to a hydrogen. So that's the carboxyl group. And then the amine group is actually a nitrogen connected to a hydrogen and to another hydrogen. Remember your bonding rules. Every carbon has to have 4 covalent bonds, every nitrogen 3, every oxygen 2. Now when you look at that structure, there's a number of things that we need to talk about. This right here on the right, the carboxyl group, is a weak acid. Okay? So this is an acid. This on the left is actually a weak base. Now, most textbooks, although things are changing a little bit, write the structure of an amino acid the way you see it here, which is wrong. It doesn't exist. This is impossible in nature. Let's see why that is in fact impossible. So most life exists at a very narrow pH range. I mean, there are extremophiles, things that live in extreme environments, but most living cells, certainly human cells, live in a pH around 7, right? At pH 7, this structure looks as follows. This hydrogen, which is a weak acid, but it has now migrated to pH 7, is completely gone by the time you reach pH 7. So it's actually a negatively charged group at pH 7. Whereas this amine group has enriched enough of a basic pH to actually lose the one proton that it has, so it actually looks like this. Has a positive charge, an extra proton there. Now, if you look at that, we can actually explain individually the two ends of the molecule and then combine them to understand the whole behavior of amino acids as both proton donors and proton acceptors. So let me put here a series of events at different pHs, and this is beautifully explained, by the way, by Buffers and by Henderson-Hasselbalch. We're going to start our look at the structure, at the real structure of an amino acid at a very acidic pH. So we're going to draw the structure of glycine in this case at pH 1. Then we're going to draw it at pH, I'll tell you which one is next, and then pH 7. And then at pH 14. Very basic. So at a very low pH, there's a lot of hydrogen in the environment. So all of the protonatable or being able to be protonated groups are going to be charged with protons. In other words, the structure of an amino acid like glycine at pH 1 looks like this. It has that structure, with this being a positively charged group. So the amine group is protonated, the carboxyl group is protonated, because there's plenty of protons around. Very acidic environment. Now, it turns out that these two are independent from each other, and each of them have their own pKa. They have their own Ka value. So the pKa of this group is different from the pKa of this group. And you're going to tell me which one is more acidic in a minute. I don't remember the numbers, so I need to look them up. pKa of glycine, maybe pKa's. Okay, glycine. I have it as 2.35 for this. And for this, I have it on this table. This is from Vanderbilt University as 9.78. Okay, so now from the previous discussion, you know that the lower the pK, the stronger the acid. The stronger the acid, the more readily it's going to give off protons, or the sooner, if you will, as you start changing pH, or as you start titrating them. So this is a stronger acid than this. In comparison, this is a very weak acid. In fact, we called it earlier a base. So this is very, very weak compared to this. Now, at pH of 1, that's what exists. At a pH of 7, it exists like what I put there. Both, and look what is happening. So by the time you get to pH of 7, this proton has all gone, has all left. Remember, God, I get overwhelmed because I want to tell you everything in one breath. I told you earlier that a buffer is really good at a pH value equal to its pKa, right? And then plus or minus 1 or 2 pH units away from that is still buffering. Well, at this pH, at a pH equal to the pKa, the amount of COOH and the amount of COO minus is equal, 50-50. You can prove that to yourselves using the Henderson-Hasselbalch equation. In the Henderson-Hasselbalch equation, you have plus log of A minus over HA. If these two values are the same, let's say 3 and 3, this becomes 1, log of 1 is 0. So pKa equals pH when these two values are the same. So what happens? At a pH of 2.35, 50% of all glycines are going to be COOH. 50% of all glycines are going to be COO minus. But as we keep increasing the pH, when we get to pH 7, they're going to look all like this. So this proton is gone. It has been given off. What happens if you keep increasing the pH, asking for these protons to leave? Well, when you get all the way to pH 14, the amino acid looks like this. All of these protons are gone now because the pH is beyond 9.78. At 9.78, 50 is like this and 50 is like that, 50% and 50%. That's the equilibrium that we are looking at here. We're going to explore this in a lot more detail. I just want you to be ready for the next homework. Now, let's look at the charges. So the amino acid is never, ever, ever like the books write it. This does not exist. I mean, it does, but it doesn't. You can actually make a calculation that tells you that 1 in like a quintillion molecules are like that. And that's because there's collisions. There's things colliding with each other at all times. But let's revisit this transition. And let's also do something about charges. At pH of 1, this is the way the molecule looks like. Protonated in the amino group, protonated on the carboxyl group. But what is the charge of this molecule? If we add charges, +1, and that's it. So the charge of this molecule is +1. What is the charge of this molecule at pH 7? +1, -1, 0. So the charge is 0. And what is the charge of this glycine at a pH of very basic of 14? 0 and -1, -1. This property allows you to see that there's a point in which the charge of the amino acid is equal to 0. And that point is called the pi. The pi is defined as the isoelectric point. Isoelectric meaning same electrical charge or electrical charge of 0. And guess what? It's not 7. But let's see where it is. So how do I calculate the pi of glycine? It's going to be the pKa of the carboxyl group plus the pKa of the amino group divided by 2. So 9.78 plus 2.35 divided by 2. What does that give you?
6.1?
6.1. 6.06 maybe? Okay, so let's put it with the number of significant digits that we see here. So 6.06. That actually tells me that at pH 7, actually there is probably a little bit of this, a little bit less of that than what I'm saying. At pH of 6.06, it's exactly like this. All right? That we're going to pick it up in the next class. Well, not exactly at that point, but somewhere along those lines, because it's going to help us understand. So please, when you start working on the next chapter, keep in mind that these guys are weak acids and weak bases, that you can treat this group independently from this group in isolation. So you look at part of the molecule and then part of the molecule, and then you combine your observations as a bundle. Oh my God, thank you for putting up with me for this long time.